morning. Good morning, everyone. Hope you okay. You're fine this morning for our fourth day of Imagination Week. Again, three conferences today. The first one is right now on robotics. The second one will be held today at 1:30 about a woman conceived in Singapore. And another one will be tonight about chocolate. It's before I will just remind you just after, but at the end of the conference, we all go together to the third floor. We didn't do that at the beginning of the week for the newcomers as well. We didn't do it all together, but we want you to have a photo group all together. So please, at the end of the conference, at 10, we go upstairs all together at 10:30, and some people from the staff will help us just to have a picture for us. So to start the conference, we have a chance to welcome Marcelo H. Marcelo H received a degree in mechanical engineering from the La Salle University in Philippines and University of Hawaii in US. His PhD is in electrical engineering from University of Rochester, US. In 1989, he joined the Department of Mechanical Engineering of the National University of Singapore, where he is professor and director of the Advanced Robotics Center. His research interests span the area of robotics, mechatronics, autonomous systems, and applications of intelligent systems. He teaches robotics, applying electronics and instrumentation, computing, design, and other related topics. In addition to academic and research activities, he is also actively involved in Singapore robotic games and is founding chairman at the World Robot Olympiad as member of its advisory council. Please welcome Marcelo H.
Okay. Thank you, Xavier. Thank you. I have. Okay, good. Good morning, everybody. I'm very happy to be here to share with you my thoughts about robotics, and hopefully after my talk you'll be so excited about robotics. I came to Singapore in 1989. I grew up in the Philippines. I'm 100% Chinese, but grew up in the Philippines, spent 6 years in the United States, and then came to Singapore in 1989 with the primary purpose of starting robotics in Singapore and to make Singapore a smart city, smart nation with robotics is a key technology. So I'm a very informal person, so feel free to comment anytime. No need to wait till the end. So feel free to interrupt me anytime. Robotics revolution, because I think we are in the start, this is quite timely today, is the start of a transformation, a tipping point, some will say, of robotics. Let's look at first how robotics started in industrial automation. Industrial robotics, you see the robot inside welding cars. This is in Detroit, Michigan, Detroit area in Michigan, United States. People are outside, the robot is inside a cage. There's a gate, a door. If the door opens, the robot shuts down. This is sometimes called a lights out factory because the robot doesn't need to have eyes. Complete knowledge of the environment is known. The robot knows where the cars are. The robot knows where to put its hand to weld. So it doesn't need to see because it knows exactly what to do. Humans are kept outside because once humans go inside, they will move things around. And once you move things around, the robot doesn't know because it doesn't have eyes. So it will still continue welding. And we don't want the robot to weld a human being, right? So that's why it's safe. So that's why it shuts down the robot. Up to today, this is happening today. It's very exciting. It's working, right? But we are at the moment of great opportunities because from here, in the last 30 years to now, we have seen many new applications in the last 3 decades, right? Let's start with here. This is the primitive form of Iron Man, right? It's a wearable robot to help you walk farther, to help you climb mountains, and an assistance device. HAL means hybrid assist limb. This is already commercial, but how come we don't see it everywhere yet, right? It's hybrid assist limb by Cyberdyne because it's commercial, but at the same time it's a bit prototypish, right? It's only research institutes or some hospitals, rehabilitation centers use it. here, the robot is inside the human body. This is the Vinci Robot. It's for medical applications, for surgery. This is 2 arms of the robot operating, and the surgeon is using 2 joysticks here. Left arm controls this. Right arm of the surgeon controls the right pincher or joystick. And he looks at a screen. This is what he sees. It's operating like using a minimally invasive procedure called something like laparoscopic surgery, where you have 3 holes, left arm, right arm on the patient, and a middle hole for the camera, right? So he's doing it. It's almost like playing games, right? You're using your joystick, opening, cutting, and doing this, but you only have visual feedback. Yeah? You only see things. Imagine you're cutting meat. You're preparing some steak or some pork dish or some beef. You're cutting. You're using only your eyes. You don't feel the cutting forces. Isn't that a bit scary, right? But it's still working. Yeah? And the newer version of Da Vinci by Intuitive Surgical, a company in the Bay Area, is they're going to have haptics feedback. Haptic feedback means a joystick with force feedback, so you can know as you're cutting it, right? And that's very important. Here, the robot is inside your home. Among all these applications, perhaps this is the one that's consumer type or most pervasive. Robotic vacuum cleaner. This is the Roomba. I have this about 15 years ago. Surprisingly, it works quite well. It just goes around vacuuming the floor in your room. Right? Here is the robotic car in Singapore. 10 years ago, we became very excited about here. And we are in the One North area. One North area is one of the first test areas of robotic vehicles. You may have seen cars, the so-called robot taxi, driverless cars. You still see people inside because there's still a safety driver, but they're not holding the steering wheel. Because Singapore is very interested in autonomous vehicles as a public transportation system. Last year, the government has already announced they have expanded the area from One North to the whole western Singapore, starting from where we are all the way to the Tuas, near the Malaysian border in the west, as a test area, or not really only test, it's a allowed area for deployment of self-driving vehicles. So that's the robotic car. This is a vehicle from Google. The computer, these are the sensors on top. And the Honda robot, the Asimo, the humanoid, social interaction, companionship, not only for physical assistance, but social interaction, even as a communication device to your loved ones in the remote areas or far from you through interaction. Imagine perhaps one day we can do a conference call, but besides hearing and seeing, the person remotely, your loved ones, can use the robot to touch you, and you can have a remote hug, remote feeling, and remote kiss, remote whatever you want to do, right? So that's it. Now, all of these applications, if you contrast it here, what's the commonality? Right? I hope you see the difference. The commonality about all these applications is the human-centered nature, right? As opposed to here where the human is out. So I think why I call it a revolution, because this really will change life today, right? How to bring robots from here to be centered around humans, helping humans. If you look at how technology helps humans, the robotics perhaps is the ultimate machine or ultimate tool that will make our lives much better, right? So I call this everyday robotics. That's why the revolution is really robotics in our everyday lives, right? Everyday lives, not here. This is not everyday lives because we don't live in this structured environment where human and robot are separated, right? This is actually only a small part of the world. What's everyday life? Everyday life is something like this, right? The grocery aisles in your supermarkets, the shopping mall, and many more. For example, the airports we have, right? The hospitals, inside the hospitals, our homes, our old age homes, our caregiver homes, a home for the aged, or our parks, our entertainment areas. So everything that's non-industrial. So on the right is anything outside the factory, and this environment is characterized by unstructuredness. Unstructuredness means things inside this environment are not exactly known. You don't know exactly where they are. You don't know exactly where the aisles are, where the shelves are, because they may move around. It's almost like if you move to a new home, it's structured because nobody's living there, right? But after people live there for a few days, maybe even a few hours, things start moving around, it becomes unstructured because of the human being, right? Because the world is designed for us, human beings, and we are inherently messy people. Yeah, if you visit my home, you will know that. Visit my office, you'll know that worse, right? Okay. So there's a lot of human-robot interaction that's needed in such environments if the robot is going to help us. So we need to move. These two arrows is really the research challenges today. How to bring this usefulness here into here, moving from factories designed for robots to robots that operate in the natural environment without having to modify the environment. Why? Because the environment is built for who? What do you think? Environment is built for us, human beings, right? So we want the robot to operate in that environment without the need to change the environment because of technology. A good example of this, I think, is our mobile robots. Mobile robots in the earlier days, when they're inside factories or inside anywhere, for them to move around, to do material delivery from A to B, you need tapes on the floors to guide them, right? They're sometimes called automatic guided vehicles. All the robot sees, looks at the tape, and follows the black tape on the floor, thus modifying the environment to make the robot operate in it. But you don't want to live in a home that there are tapes all around the floor to guide the robot. And if you want to change the path of the robot, you need to remove the tape and put new tapes, right? In the United States, in the Berkeley area, in the San Francisco area, they tried autonomous vehicle in the 1980s. It's the PATH program, where they embedded the highway with magnetic devices. It's like, think of it as magnets all over the Bay Area in the highway. So the robot looks at, instead of a tape, looks at the magnet, reads the magnetic field, and guides the machine or the self-driving vehicle. But it's an experiment, but now they're not doing that anymore. Why? Because today we have technology that you don't need the tapes anymore. Like human beings, I can go to that exit door without having a tape, right? How? I know the environment. I can know where the wall is. I know where the steps are. So I can use the natural features of the environment to know where I am and to navigate, to operate properly. So that's an example on how robots can be more intelligent to operate in our natural environments. So what are the compelling applications? We want to be happier, right? That means we don't want to do mundane, boring tasks. Humans are too intelligent to do these tasks. So I call this the 5 Ds. There are tasks that are dirty, like cleaning toilets, tasks that are dangerous, maybe in high buildings, cleaning walls in high buildings, or in nuclear plants, for example. Demeaning, degrading, humans, it's not worthy for humans to do it, right? And the 5th D I started working on 10 years ago. Guess what? I sort of gave a hint. It's driving vehicles. The driving vehicles. Why? Because not only it's mundane, right? It's also a kind of application, an application where I believe computers can do a better job than human beings. It's a no-brainer. Why I say that? Because computers with the sensors around the car, the sensors in the car can see things 360 degrees. Human, when you drive, you only see in front, right? But the sensors can see everything. Not only that, the sensing performance is much better than humans because the sensors in the car not only sees things, they can recognize people, cars, pedestrians, bicycle, motorcycles, and they can also know exact distances to the accuracy of a few millimeters. Right? Humans, if I see you, I don't know how far you are. I have a rough gauge only. So we see everything, right? We, meaning the computer, can see everything better than humans, one. Second, the computer doesn't get tired. It's always consistent, always reads. It doesn't get sleepy. And more importantly, perhaps the performance is consistent. The computer driving a car doesn't get emotional. Yeah? If somebody overtakes it, cuts it in its lane, it's okay. It doesn't get angry. It doesn't change its behavior because somebody did something stupid in the traffic situation. But how come we don't see self-driving cars yet? Because the challenge is really predicting human behavior. Unfortunately, in a self-driving vehicle application, you have a driverless car, but the other cars will have human drivers. You know, we all know what happens if we drive cars, especially in Asia, where traffic is quite bad. I'm in the left lane. I want to overtake. I go to the right lane. It's clear. But the car in the right lane behind me starts speeding up because it sees I'm overtaking, right? Now, if it starts speeding up, what will I do? Will I speed up more? Then maybe he or she may speed up even more, or should I give way? So predicting human behavior is really a challenge, and we're still working on that, right? So today, self-driving cars can drive well, but in a stupid way. Can drive safely as long as you don't overtake, you don't change lane, you just follow a fixed route. And if the car stops in front, you also stop. If it goes, you also goes. Then that's fine. So with these applications, perhaps we can definitely improve productivity, and especially in an aging population situation, right, where the people are getting older, the physical capabilities are less, but they still can contribute well to society to make all our lives better. So we need to have robotics to help them, right, in the not so intelligent things to do. So this is really manpower for high value added services. This is especially important in Singapore because we don't have any resource. The only resource we have is knowledge or people, right? So we need to have those knowledge and people to improve the quality of our lives, yeah? Now, when we talk about robotics, right, or any technology in general, I like to use this slide, and I call this sliding autonomy. Because the robot is a tool for human beings. That means a tool. Tool means it's going to be used by a human being. So it cannot operate by itself alone. In the ultimate case, the human needs still to tell the robot what it wants it to do, or turn it on and off, right? So there's always a machine doing it. There's always a human being doing it. If you look at the task as this is the task, perhaps the lowest level is done by the machine. The next highest level is done by the robot. So here is done by the machine, and this is done by the human, right? Let's look at a simple task of a washing machine. A washing machine is very convenient. It improved our life. In the olden days, without washing machine, you have to hand wash everything, right? So what's the washing machine today that you can buy from a department store? The task is washing machine. The machine almost does everything, right? Almost, right? You just, what does the human need to do? If this is bar here is a task of washing clothes. The human needs to do something. What? You need to set the time it needs, right, to finish washing, right? Whether 60 minutes, 30 minutes, 45 minutes. The settings of the clothes, whether it's soft or silk or heavy cotton. Many settings. And then you still have to load the clothes inside the washing machine and press on, right? So that's what the human does. The rest the machine does. It's very good. Now, technology, life is always improving. We want to go next level. We want, for the same washing machine, we want to make the machine do much more and human does less. Then you begin to think, people think, right? Oh, why do I need to still set the time it needs to wash the clothes? Can I just make the machine automatically stop when the clothes are clean, right? Why do I need to know it's 60 minutes, 40 minutes, or 50 minutes, whatever that is, right? Why do I need to know the type of clothes? Can the machine detect whether it's soft, cotton, silk, stockings, or dry fit, and automatically regulate the washing mode based on the clothes, right? So with that desired, then it's really improving the machine so that you don't need to do settings. All you need to do is load the clothes, right? So then we begin to think, perhaps I need a sensor to sense whether the clothes are dirty or not. Now, how do you know whether the clothes are dirty or not? If you have a clothes, when do you know you need to wash your clothes, right? Perhaps you smell it. So maybe we need a sensor to smell clothes, but something easier so you don't want to smell, because if it's dirty, maybe it's kind of not nice to smell dirty things, right? So what do? When you wash clothes, right, if you put it on a water and you wash it manually, what happens to the water? If the water is dirty? It's dark, right? It becomes murky. It becomes gray. If it's really dirty, it becomes black. If it's not dirty, maybe grayish, right? So then you think, maybe all I need a sensor to see how transparent water is. And now you can buy sensors about $1, even less than $1. It's a light sensor. a pair of a sensor and a transmitter, transmits light, and the receiver receives light. If it passes through a water, right? If it's transparent, yeah?
You have some clothes, they change when you put it in water,
Yeah.
the color of the water changes.
Yeah.
Not because of the
Oh, yeah, that's a good point, yeah? Then you need to have a higher technology for that, right? Yeah, because you might think it's dirty, but actually the color changed because it's a new clothes, the dye, right? Yeah, so I don't know about that, so maybe that's the reason why we don't have. So we need to have, then we need another sensor besides the light sensor to detect whether it's transparent or not. Maybe we have a sensor to distinguish between, is that color just a plain color? It's not because of dirt, right? Yeah, I don't know. Yeah, that one is an open question right now. But then you think, how do you know? How do you try to answer that question, which is a nice, important question, is you see if you're a human being, how do you tell that it's really not dirty, it's just the color running out, right? Somehow we know how to do that, right? But if you explain to people, how do you do that? It's kind of hard, right? Yeah? I mean, I'll get back to that on this is the intelligence of the machine. How do you give machines more intelligent? Okay. Another kind of application is here. A more complicated application is driving vehicles, right? Driving vehicles, the machine does almost nothing. The human does all the driving. But today, if you go down here, you have driver assistance system, which is like automatic parking or adaptive cruise control, which means the car moderates the speed according to the car in front of you. If the car in front of you is faster, you're also fast. If it's slow, you're also slow. Now there's lane keep assist. You buy any car now, these are all features available. Lane keep means even if the road is turning right, you will also turn right because you follow the lane, right? But it's okay, it works, but the human still has to make sure it works properly. Because what if the road doesn't have a lane? Meaning in here, Singapore, there is, but in the Philippines, there are many roads without lane markings, right? And so there's nothing to lane keep, right? Because there's no lane. So that's also a problem. That's why human still has to do many things. So as life improves, right? We go here, life improves, but we still have to do more. And so another arrow is keep going on. As we keep going on, right? Quality of life of everybody improves, right? And that's what really perhaps drives us as people, as human beings. Why we work, because we solve problems. We want to make life better and better. Is there an end for which the purpose disappears? I don't think so, because even the washing machine, perhaps after you have these fancy things that can detect even whether it's color or dirt, right? Maybe I would say, why do I need to still put the clothes in the washing machine? Can I have a robot just automatically take my clothes and put it in the washing machine? And perhaps maybe when I go home, somebody just take off my clothes and just put it there when I need it. And when I need to wear it, I just choose it and I just wear it easily. Another problem is ironing clothes. Ironing clothes is very, very hard to do. That's one of the most tedious tasks I hate to do, right? So can we have a robot to do that? Right? So in other words, as we achieve the goal, human beings are always not satisfied. So we raise the bar. So this task I initially said is like this. If you reach that, you raise the bar. Machines need more. Humans still need to do. So it's a never-ending enterprise, right? Never-ending job for all of us. That makes life fun, right? Okay. So how do we get there? How do we get there? That arrow, right? From industrial robots to non-industrial everyday lives, we need improvements in the hardware. I call that we need intelligent mechanics, because the hardware is a mechanical system. It does things. Like this is perhaps an example of such a hardware, because the hardware must have an arm, some kind of arm doing something, and must have a mobility. Must be on a base. So this base is here. It moves around. It's inspired by a swivel chair. It's like how swivel chair is easily going to move left and right, forward, backward, and turn, and with an arm. And we need to build this, something like this, that you are comfortable to be in your home, right? Will you be comfortable if this is inside your home? Not really, right? It looks like a mechanical thing. It's kind of scary. That's the problem. That's why we need hardware improvements, because most of the robots you see today, right, they're designed for industrial applications, structured environments, not interacting with human, right? But this is the most advanced today. This is the KUKA Aiwa. It's German. It's from KUKA. Aiwa, I forget the German word actually, but it means, translated in English, intelligent work assistant. Intelligent work assistant, and that is meant for human-robot collaboration, but it's still meant for a factory environment. Perhaps one day we'll have a robot similar to what we see in movies, like Big Hero, like Baymax, that bubbly, that like big balloon, that's a robot that you can cuddle, you can soothe, it's soft. So there's a lot of things that we need to do so that this robot can naturally operate in a safe way working with human beings. Another important aspect, improvements needed, is software, the intelligence. So we need a better body. Second, we need a better brain, right? But brain has many meanings, right? There is low level and high level if I divide it into two, but there's actually a hierarchy of different levels. So let me show you. The following slide shows you some of our work in all these aspects. This is some work people call soft robotics, because physically, the robot is made of soft materials like rubber, right? Here, this is silicon, right? And there are air chambers or lines where air can go in. The air is pumped through this hose. When you pump air, it's designed such that the air's path is such a way that it will make that finger curl accordingly. So this is designed differently from this. This curls that way, increasing curvature. This is like a snake or a tail, right, grasping objects. Right? But it's made of silicon, and the key here is how do you design the internal air channels, the structures, to make it behave mechanically in the correct way when air is pumped. Because it's air, it's compressible, so it's naturally soft, and silicon by nature is like a rubber. It's orange because we use cotton thread, orange thread, to embed it inside the silicon, because the thread serves like a spine, a structure. We have more threads per inch, it changes the stiffness. Less threads per inch, different segments of the finger is softer. So by changing the stiffness at different parts, you get it to behave mechanically. This is almost like this kind of idea of mechanical embodiment is like in the earlier days. Do you remember the soft, the wooden puppet or dolls, right? That walk, and you just put it on an inclined plane, and you just give it a nudge. It just tuck, 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 always like this, right? And there's no control there. There's no intelligence, but the mechanical structure is designed so that when you turn it on or give it a push, it will naturally do it. Right? And this is that physical environment, and they're inherently safe. These are also made of air or air activated. This is the air hose connecting to little pouches. These are made of like thermoplastic urethane pouches. When you pump air, the pouch enlarge, turn off air. So each individual pouch is like a joint. They joint connected together, and you can carry a balloon, very soft material. And here is 3D printed using some kind of rubber material, right? Most of the 3D printers uses ABS or PLA, which is hard, but there are now newer materials that's almost like a rubber band, that you melt those rubber band and make it into something like this by 3D printing, right? So they're inherently safe. This area is an area called soft robotics, air activated. Air is the main source of power. We use this for fingers, but we have also used it for arms. Perhaps one day, the same technology we can use as a wearable robot. Instead of just building the robot, you can wear something that's air activated that can help you carry heavy things, help you walk without getting tired, for example. Another kind of soft robot is double-sided tape. Double-sided tape, you can buy it from hardware store. This is one model from 3M, very high bonding tape. If you peel the top and bottom layer, it's sticky on both sides, but this is kind of rubbery. It's an elastomer, but we make it behave like a dielectric. Dielectric, we put a charge across it, and by turning on the charge, it compresses the sheet, and the sheet expands in area, right? Then you turn off the charge, the sheet goes back, right? So with that phenomena, what can we do with it? So engineering is about this scientific phenomenon, very simple. It's a rubber band. You turn on voltage, it stretches the rubber, turn off the voltage, the rubber band shrinks back to the original shape. And we can use that to make into like a worm or an inchworm mechanism or a caterpillar, how a caterpillar moves, right, by turning on and off. The first time I discovered this, or people discovered this also, is that this reminds me of our muscles, right? Our muscles, when you put electrical energy in it, our muscles extend, turn it off, it contracts, right? Or the other way around, right? It's using electrical energy. So it's up to you how you want to do this. I have a former student, actually he's from France also. Yeah, he built this to create fingers, right? And imagine you create many of them. Imagine you have an array of fingers, 10 by 10, 100 fingers, and you put it at the back and under a chair. So when you sit, that will be the ultimate massage chair. And you can control individually each finger. But like many projects, it's just a project. I'm still waiting for somebody to commercialize it. Yeah, but I don't know where that is now. That is many years ago. Because if you look at our massage chairs, they're not really so good, right? They're very hard, right? But this, if they're made of soft materials, that will be really the ultimate. Imagine the applications. This can be in your airline seats, your driver seats, passenger seats, everything. The only drawback here, people may be scared, use this because the voltage needed to create the actuation. Can anybody guess how much voltage is passed across here? High, very high. Well, it's in the order of about 5,000 to 10,000 volts DC. Yeah? But there's no current flowing, very, very little, because if you just create the electric field, there's nothing that passes through. It's a rubber, right? So the current is very low, so power is very low. So even if it's 5 or 10,000 volts, we can power it from AA batteries. Now you can just buy off-the-shelf electronics to power it. So it's very nice. So on and off, you can see the same thing can be used in the reverse. You stretch it, it generates voltage. Here you give voltage, it moves. Here, you move it, it generates voltage. So what does it mean? This can be an energy harvesting device, right? Perhaps one day you put many layers of it, put it under your shoe. As you're walking, yeah, you're charging your phones. Put it under the roads. As the cars pass through the road, especially in the traffic light, when the car stops, there's kind of some impact, right? The change in there's an deceleration. That action can charge these devices that will power perhaps our lampposts in the future, in the roads and our traffic lights. Yeah? So it's quite exciting. So this area is called soft robotics. And if we here, this is actuation. The soft materials being moved through electrical means, previously through air, pneumatic. You can also embed sensing in it, right? Using the same phenomena, you can know how much the thing has shrunk or expanded. Let me go to mobility now. I showed you the mobile robot earlier. This is a more detailed view. We're inspired by the swivel chair, right? So this is a swivel chair that we sit, and we sit because it's so mobile, right? So can we make a mobile robot like that? And we have actually done it. These two, one motor here, and by controlling these two sets of wheels, 4 motors, you can make this robot move like this or like this. Right? Now he is controlling it using a joystick here. And this can also turn. Right? So it can do X, Y. It's like a human, right? I can walk like this. I can walk like this. I can also walk like this and while turning, right? So this can literally dance the waltz. Yeah? It's very nice. Imagine if our cars were built like this. What does it mean for parallel parking? You're parking, you want parallel, you just go like this. Right? Wouldn't it be nice? I wonder why they don't do that. Huh? But it's interesting. We have done it, and it can be doing this. Because you need an arm, whether it's soft or not, you need to give it mobility. Of course, this is not the ultimate in mobility. The ultimate in mobility is what? Our legs, right? Because this cannot climb stairs. But the leg is a bit too hard yet today. So let's if we can solve the problem on all plane, let it take an elevator, then it will work already. So that's another kind of hardware improvement we need to give mobility to the arm. Let's talk about intelligence. This is the lowest form of intelligence. I call it reflex action. It's almost like if I'm a robot, I touch something hot, I will immediately move my hand out, right? If you're cooking and something, oh, ouch, you move out. You don't think, oh, ouch, what do I do? Then you move out, right? You don't do that, right? Because this is automatic. So this is the lowest form of intelligence. And we use that also to do things like this. This is a polishing application. You want to polish your car. In this case, you're polishing the canopy of an F4 aircraft, doing this. And the human is still moving. Rodrigo, my student, is moving this base. But the robot is blind, but it just feels the surface. If it needs to turn right, it will turn right, turn left, it will feel. Building upon what it can do here, right? And this is showing how much you can do with internal sensing, without eyes, just by feeling. If I ask you to clean this table, I don't really need to know my eyes. All I need is feeling my hands to clean it, right? And if it's the end, I know I'm at the end. And we have extended that more recently with a better robot. This is a very old robot that we can do things like this, 90 degrees, and where there's a sharp discontinuity. Yeah, most robots today, when they do this, applying a force here, at this corner, it will have chattering because it will know it disappears from the contact, then we go back and ta-ta-ta-ta before going out again. Stop, sorry. And we use that to this is actual polishing. I call this reflex action. Yeah, and it's like moving while feeling. It's very important. And this is done without having a brain. This because it's automatic. Actually, studies have shown biological beings have many levels of intelligence. The lowest level is like automatic, which I call reflex action. I'm sure you have heard stories of a chicken being beheaded, and the chicken still runs around, right? And how can it run around? It's a very complicated motion because there's something in our spine, right, that generates patterns. It's called the central pattern generator, right, that allows us to do automatic movement without the brain controlling it. So this is reflex action. If you think about it, this is movement without external sensing, just by learning, feeling your internal states of your body. If I want to move my hand horizontally, I can move it with closing my eyes because I feel my joints, right? But if I open my eyes, of course, I can do a better job drawing a straight line. Let's go higher level, jump fast forward to the highest level, which is the intelligence. There are always 4 things happening, or at least three. The first 3 are here. First, you have to have sensors to understand the environment, to give meaning, to know the context. If the sensor is my eyes, I see here, I should know I'm in a classroom. And with a classroom, that gives hints what I should do in a classroom, right? And that gives hints to my planning and decision making, how I should behave in a classroom. And after I plan and make decisions, I execute it, number 3. Then I learn from it, and I keep continuing doing that. And we're doing this every day, right? Everybody is doing this every day, and we learn how to do things better and better, right? Now, how do we do these 4 things? Right? There are 2 basic approaches in intelligence. This is the high-level intelligence. One is the model-driven approach. We create a model of the world. A model is a mathematical model that relates the input to the output, right? If I have a mathematical equation relating input to output, if I want the output to be some desired output, I can solve the required inputs from that mathematical equation, right? No problem. But the problem is, it's very hard to get this mathematical equation, right? For example, a simple output of the forces in my muscles to make me walk like this, right? To do that, to create the mathematical model, I need to know my weight. I need to know the center of gravity. I need to know how many limbs I have. I need to know how much blood is flowing because that changes the inertia of my body, right? And that's almost impossible to compute, right? So what we do an approximation. Because the approximation, then our equation is not accurate, so it will not create the desired output. So we measure what is the actual output compared to the desired output, and we give feedback to improve our performance. And this has been happening for ages. And engineering has been all about this, but there are just so many problems, even with the output very, very wrong, right? Even the output is very wrong, you still cannot correct it. Yeah? It just takes too long. So today, we have a different approach, which is called data-driven. Can we learn from experience? Right? A very important example here is, for example, this physical phenomenon you want to understand is recognizing a dog from a cat, for example. If the input is a picture of a dog, a picture of a cat, the output can be just an identification. Is it a dog? Is it a cat? Now, how do you write a mathematical model? How do you derive a mathematical model? The input is a picture. The output is either dog or cat, or A or B, right? How do you do that? You can see how complex it is. And people have tried that. You extract the features, the eyes, the nose, the mouth, right? And try to find how these features make into a dog and make a cat. But do you think human beings do that? Not only for recognizing dogs and cats. Let's say detecting a male and female. If you ask me how many male and female are here in this classroom, I will know, right? But how do I know? I don't know how I know, but I know, right? But it's very hard to put it into detailed steps. How I know? Because I've lived enough in this world. I have a lot of data. It's a learning from experience. How to learn whether somebody's dog and cat is as follows. How humans learn. You give it many pictures of dogs. Say that's a dog. Many pictures of cat, that's a cat. And that's all there is, right? With enough pictures of dog and cat from experience, you give a picture of a new dog, it will know. Same for male, female, right? A baby wakes up, sees mommy, and then sees daddy, and pretty soon, without telling the baby what the world is, the baby will know that there are two kinds of people. There's one called male, there's one called female. Now we ask the baby, how do you know that? I don't know, right? But I just know there are two kinds. Because the brain has an incredible way of doing pattern recognition, and the label of that being male or female is artificial. We just call it. It's a human artifact, right? Dog, cat, it's just language, right? Dog, cat, only English. In French, it's different. In German, it's different. We just as good as saying this is A, this is B, right? So can we give that intelligence to robots today, to machines? And the answer is yes. And how we do that is through something called a neural network. But before that, among these two approaches, which is better? Which is one we should use, right? I think the answer is we should not debate which is better. We should use both. If we have a model, we should use it. Why not use it, right? But we know the model is not accurate. So instead of doing feedback, we use the data to improve the model. So it's a hybrid approach, right? So how do we learn from data? This one is easy. We just derive mathematics, right? From Newton's laws, scientific laws. But data, how do you know, right? How do you learn, right? So we know the brain is doing it somehow. So the primitive approximation of brain is a neuron, a brain cell, right? So this is, oh, sorry, not this one. How come it went? Yeah, this is the brain cell. Yeah, so this is an approximation of a brain cell. It receives signals from other brain cells through a synapse. And depending on how much signals it receives, it gets excited or not. If you look at the highest level, it's like when you're watching a movie, sometimes you fall asleep, right? Because it's not exciting, right? But if it's a horror movie, maybe you won't be able to sleep. So it depends on the signals you receive. This electrical signal gets dormant or hyperactive, right? And it sends to other signals. So that's all we know about the brain. Very simple. So can we emulate that with a computer? And Bernard Widrow from Stanford did it in 1960, right? It's called adaptive linear element. This is the brain cell. It accepts inputs from other brain cells. It just sums it, right? But before it sums it, let's say this x1, x2, x3, it multiplies x1 with w1, a weight, x2 w2, x3 w3, and this is a summation of xi wi. So it's an aggregation, and depending on what it sees the teacher is the world, right? Let's say you show it a cat, it's this, then it says, okay, that's the first time I see it, it's a cat. I get excited, oh, I saw something new, I don't know what it is. Let's call it object A. So it gets excited. You see another cat, oh, I've seen it before. I don't get excited, I sleep. But you see a dog, I get excited. In other words, depending on the environment, the teacher, and the input, it creates an output. The output is either super excited, hyperactive, or super sleepy, dormant. But today, we think, why not half excited, half sleepy? So this can be a continuous number. And instead of a step function, you can have a hyperbolic tangent, sigmoid function, a ReLU, many other terminologies. And if you put them all together into a Madeleine, a multi-layer, this is in the 1980s, you give birth to the neural network. Right? A neural network is a network of neurons connected. And what happens when you learn from data experience, it learns what should be the weights, what should be the shape. Right? These are called the hyperparameters of neural network, so that it knows how to distinguish a dog from a cat. So it knows to do things that's very hard for us to explain how we do it. Right? It's like learning from experience. Now, it became very exciting in the 90s. Right? I remember when I moved to Singapore in 1989, my first project was a neural network. But during that time, the results were not, it only works on very small toy problems. But for real problems, it's very hard to work. Why? Because you need many, many neurons and many layers of neurons. Right? So it became not so exciting. Right? So people lost interest in the early 90s. But in the 2000, the interest went up again. Why? Two things happened. In the 1990s, this is the birth or the explosion of the internet. In the internet, people have social media accounts, and people upload everything in the web, right? So there's a lot of data. All of us have Google Photos account, I'm sure, and even all the accounts we have so much data there. So because of availability of data, there's a lot of training that can be done. Because for this to work, you need to learn from a lot of data. Number two that happens in the world is explosion of computers, right? Meaning faster computers. In the earlier days, the computers were done for graphics programming, right? For games. But the same gaming cards, right, can be used to compute this. Why? Because when you want to use virtual reality or simulation, it's an inherently parallel processing algorithm. So if it's parallel processing, the same hardware can be used to do the neural network. That's why today, NVIDIA is a company that makes graphics chips for gaming. Now NVIDIA is now perhaps the world's number one of the top 2 companies doing artificial intelligence. And to get away with the bad history of neural networks, because everybody was not excited, they say it's too hype in the 90s, they don't call it neural network, they call it deep learning, right? Which is exactly a neural network. It's just a change of name. Why deep? Because there's so many deep layers of neurons connected to each other. So the remaining 5 minutes, I'll try to speed up, is some applications. This is our work in self-driving vehicles. We call it multi-class mobility, right? You book the car using an application like this. And it tells you the car is there. It goes to where you are. Unfortunately, the car doesn't go up the escalator yet. Yeah, but so you have to still go down to the building, the lobby. You want to go to Kentridge Station, which is a train station near the hospital. But this car cannot go on the roads. It goes on a pedestrian environment, right? So it just goes to meet a car, another car, that's meant for the roads, right? So it goes through buildings. This is 2 times the speed. It goes to this is in university town. This is how much sensors, how far ahead the sensors see. This is where the car, all the dots there are the people around it. These are lecture theater. our canteen, and it meets Scott, a car. All our cars are named by my first student who worked on it. This is a shared computer-operated transport. And this is the driver jockey, Damien Che. Both of them and Tawit, they're all working from a startup that came from my group in 2013 called Autonomy. They're right here in One North, in Fissionopolis, and blocks, one of the purple blocks. No? You go in, you confirm with your PIN, I'm the one who booked it, you can change your destination, then you say, yes, let's go, then it just goes by itself, right? So we were calling this the last mile problem, right? Because it's not for long distance driving, it's just going to the nearest train station. And Singapore is very interested in this because we want to use this as a public transportation system. I think many years ago, Autonomy had like an Uber-like application in One North where you book the car to go within the One North area and it's driverless. Yeah, but they stopped that now after they had the first accident in Singapore. Yeah, but they're resuming it, but now it's much wider. In 2022, most likely 2023, we'll have this full deployment in 3 districts in Singapore, right? A driverless taxi, driverless bus, different sized buses, where we call them level 5 automation, where there's no safety driver inside. Yeah. One of the challenges we're facing today is how to deal with rain. Rain is a very hard problem, right? And this is a very good application of deep learning, right? If you're a human, yeah, please. Yeah.
In the picture before,
Yeah.
you said the car was automatic, but
Yeah.
the passengers still have to sit in the driving seat.
Yeah, the passenger seat, yes. Because the driver is still needed to be there as a safety driver.
Okay.
Yeah.
It means that you can stop the automatic
Anytime, it can do automatic work. That's called level 3 automation. But Singapore wants to work on level 5, 4 and 5. Level 4 and 5 means there's no more safety driver, right? And passenger doesn't need to operate. And that will change the concept of the car. You don't need a driver's seat. So the car can be just a small, like a limousine, or maybe even have a bed or table inside, whatever you want to do there, right? But we're not yet there. Nobody in the world is doing level 5 yet, or has achieved it yet. So rain, our sensors do not work on rain, right? Because we get confused by rain, right? But humans are very good at this, because if I show you this, I ask you, imagine the scene without rain. You can always have this in your mental imagination, right? Right? So how do we do this? Because you have seen enough pictures, right? So what we do, we use deep learning, show it a lot of pictures of rainy and non-rainy images, right? But if you show a lot of pictures, I cannot get my student to just go outside the lab, wait for it to rain, take picture, take picture. That would be, we need about 10,000 pictures, right? So what we do, we synthesize rainy data, right? We just use a simple application like Photoshop. Right? So from a clean image, we use Photoshop to fake rain. This is really the ultimate in fake news. It's fake data. We pretend there's different levels of rain, as shown here. We synthesize different levels of rain. GT is the ground truth, a clean image which is true. We add 3 levels of haze or fog. We add different levels of rain, light and heavy rain, and we create about this amount of data. And we train it using a deep neural network, not so deep, only a few layers. We use a hybrid approach. We have some mathematical model of how rain distorts images. We combine that with a neural network model. This is a hybrid approach. And we tested it, and this is the results from testing, right? This is done automatically. From here, it creates this, here, this, which is surprisingly well, right? We don't know how it works, really. But at the same time, we know how it works because it's a neural network, but we don't know really how the neural network works, right? We just optimize it. It's just a training problem. But this is on synthetic data. In other words, data that are fake. What's more interesting, we test it on real-world data in Singapore. This is real-world data in Singapore. With this rain, we're able to do this from here to here, here to here, here to here. So very exciting. We move one step above, closer to how we can solve this. Another problem is this. How does the robot know that these two are the same place? You know where this is? Yeah, this is a train station in downtown Singapore, this Raffles Place, right? Here and here, we know they're the same. But no computer vision program will know they're the same. So the question is, how do we train a computer, or artificial intelligence, to know, to remember only the permanent features of the environment, not the dynamic, right? For example, if I go to this room tomorrow and it's empty, I know it's the same level 1 classroom 1, right? I know, but a computer, if you compare pictures, it will be very different, right? How can the vehicle learn places? This is very important because we do not use GPS, because GPS is not reliable. So how we want to localize, know where we are, is just by looking around, right? So our approach is use a neural network to tell it, all of this should create this, right? Yeah. And how we know, we don't care how. We just give it a lot of pictures and learn the weights there. Then so next time we show this, it will create a clean image. So I know I'm in Raffles Place. So we're working on this today. Can we do away with pre-mapping? This is a map of our university town. Right now, self-driving vehicles, when they work, before they can work, somebody has to drive it manually in a new place. And it creates a map. And next time you bring the vehicle there, it knows where it is. But humans don't need to do that. This is my first time to ESSEC in Singapore, but I just look at a map like this. I know where ESSEC is, then I can do it, right? Why? Because I've lived long enough in this world, I can associate map features with what I see in the real world. I can know this is an intersection, this is a corner, this is an entrance. So we're trying to train a neural network to do that. We have some interesting results also on that. This is our project with Singapore Technologies Engineering, because I said in 2022, Singapore wants to have public buses that are driverless. So this is using our sensors. We can see other vehicles. This is the driverless bus. We're not yet so confident. This route is from Jurong Island to Boon Lay, right? It's not heavy traffic, but we can detect cars. And we can try to do a very simple prediction. And this is a very simple prediction. If I detect a car, the dot, dot, dot in front of the car is what they will be at, where they will be at after 1 second, 2 seconds, up to 5 seconds. Very stupid, right? Because it just assumes it's the same velocity because we don't know, right? But what we're doing today to make it more intelligent, we give it enough videos of how cars behave, and localization. By remembering where you are, you have context awareness. I know I'm near a pedestrian. I know I'm near an intersection. How do we combine this with observing how cars behave to predict human driver behavior, right? Okay, so let me summarize with this slide, sort of a summary today, right? We have a task that the robot needs to do. We can do very well, control the forces of the robot, the motion is very well, but still we cannot execute the task very well yet. We can only execute the task very well in the factory, structured environment. Why? Because we need improvements in the hardware. I mentioned about that, inherently safe, soft robotics. We also need a lot of improvements. Here is all about intelligence. We solve this question mark by linking perception and action, and deep learning is a very attractive way to do it, right? Because we learn from data, because modeling is just so hard. And how learning can be used to keep improving how we do this, and all of this forms our knowledge base of how we operate. Thank you very much. Thank you. I'm sorry it took longer than expected, but
Perfect, Marcelo.
Thank you.
Very much. We can open the floor for a few questions.
that's the most important questions. Yeah. Please.
Isn't the fact that we can't interpret how the neural network is working a huge problem to implement robotics in reality?
Oh, no, not really. Some people feel that. There's an active research called Explainable AI. In other words, making the black box not black, right? But I'm not so worried about it, because humans do things, we don't know why we do it, but we still do it, right? And we can still operate. In other words, the ultimate answer there is, who cares? That's how it works. You care because you want to make sure it always works.
Yeah,
No.
because let's say that AI do a bad action, for example,
Yeah.
and we can't justify why it did the bad action. We have
Yeah.
to justify it.
Yeah, we have to justify it. Correct. Yeah, that's correct, yeah. But maybe it's very hard to do that. We don't know how to justify it. That's why people are working on explainable AI. Let's say a human does something bad, right? And goes to the judge. And the judge tries to understand, right? You think the human will be able to tell you? Maybe even if he tells you, may not be the real reason to, right? He committed the crime or whatever. So it's really a mystery, right? But that's the situation, right? Maybe we won't be able to know that, right? But you're right, it's useful to do that, but that shouldn't prevent us from using the technology today. Yeah. Yes, please.
We have to
Okay, sorry.
other questions. Olivier?
Yeah, maybe later.
Yeah.
Hi. My question is related to the robotic products.
Yes.
Because many people agreed, saying that by 2050, I think, we could reach it, which means that robots would try to destroy us, to protect us.
Oh, no. Okay.
And I'm asking a question because you're a specialist, I'm not. Well, what's your point of view about it?
Yeah. I don't think robot will destroy us. Yeah, all this science fiction, like the movie iRobot, for example, I think that will never happen because humans is still in control overall, right? Or certainly not in many of our lifetimes. Yeah, because it's just too hard to do that, right? One thing that humans have that robots don't have is what's the difference between robot and humans, for example, right? Some people say it's the soul, whatever that means, but that can be also programmed as an algorithm, right? But I think robots are just too far behind human capabilities. Perhaps one day in the future, perhaps, but I don't see that happening really. Yeah. Because it's just too hard. One thing that's different that you can program is the organic feature of human beings or biological beings, the ability to reproduce. Yeah, robots cannot do that. Yeah? Life. Yeah. Yes.
Thank you for your presentation.
Yeah.
So what's your take on the usual criticism of technology that's going to destroy jobs, worsen health and social lives, and create maybe class divisions between those who can afford and can't afford the technology?
Yeah. I don't agree with that because if they take away your jobs, right, my answer is they ought to take away that job. Because you will do, once I give you the alternative, it's like changing your job scope. Instead of doing something really mundane, right, let the robot do the mundane, and instead you doing it, you'll be free. Once your head is free, you will do something more meaningful. The very important question is for drivers. If driverless cars, what will happen to the drivers, right? Will they all be jobless now, right? Yeah, maybe they ought to be jobless because they're more intelligent. Maybe they will be the one in the control room doing the fleet management system to make sure that the cars behave properly, doing exceptional in the comfort of an air-conditioned room. For example, during war, soldiers, right? You don't need to be killed anymore. You don't want to be soldiers, but you're now in the comfort of a nice control room, air-conditioned, but you're controlling all the weapons of whatever that is. Which kind of interesting too. That changes the mentality. Okay.
Last question?
No? Okay, thank you.
I was asking the question about how you interpret, because even for a really simple task, like for example in a bank, if it's an AI that say whether or not you attribute credit to someone or you lend to someone, you need to explain why it agreed to lend or why it didn't agree to lend to that people,
Yeah.
to that person.
Yeah, that's right. Well, it's all going back to the explainable part, right? Explainable, right now the neural network is not explainable yet, yeah, but people are working on that. But AI is not only neural network. There's many AI, that machine learning, right, that is not black box. So that can also be used, right, to do that. And For example, the neural network, the many layers, right? Even going back to the neural network, if you look at the data in individual layers, you can get some clues on how that's done. So people are working on that. For that purpose, it's important to have it. Yeah, correct. Yeah.
Thank you, Marcelo.
Okay, thank you. Thank you.